Welcome back everyone. In this lecture I will continue to give more examples of groups. Okay, in this lecture we will actually see some groups that are coming from elementary number theory. So especially we focus on subgroups of the group of integers. Okay, so let me first recall. So what is the group of integers? So this z plus, so that is what we denoted it by the group of integers with respect to addition. The group of integers with respect to the addition. Okay, so all of you know how the addition works in the group of integers. Okay, given any integer n, the inverse will be minus n, 0 is the identity element. Okay. So now what we are interested in, so we are interested in some subgroups of these integers. Okay, let me first define what is a subgroup. Okay, then we will actually look at all possible subgroups of integers. So if you have a group, let us say G star, and then we want to talk about subgroups. Okay, so that means they are first of all subsets of G and that satisfies some specific properties. So what is the property? So you start with a subset of G, again you want it to be non-empty subset. So now what you actually claim, this subset is said to be a subgroup of G. So then this binary operation, so this can be restricted to H cross H. Okay. So then this becomes a priori map from H cross H to G, but what we expect if this H is a subgroup, if this is actually a map from H cross H to H, and with respect to this map this actually becomes a group. Okay. So a non-empty subset H of G is said to be a subgroup of G if the following conditions satisfied. The first condition, you take that star which is the binary operation that is defined on G, which is a map from G cross G to G, that you restrict to H. So then you actually have a map from H cross H to H. That means if you take two elements from H, call it A B, then A star B should be again element of H. So that is the first condition. The second condition, this star restricted to H cross H with respect to this. So this tuple, okay, should be a group on its own. Okay. So what is the meaning of that? So that means you have the binary operation defined on H, with respect to that you should have associativity, existence of identity and existence of inverse element. So if you think about it, associativity we already have it for star itself or as a map on G cross G to G. So the restriction also will satisfy associativity, there won't be any issue. Okay. And since it has to be a group on its own, so you need to have identity element. So one can easily prove that the identity element of this H will be same as identity element of G. Okay. So that is something you can take it as exercise. And then what else is there? You need to actually say only the inverse of given element should be there inside H, and inverse of any element of H. So as a group there is this element none. So with respect to H and with respect to G there are two inverses you can possibly think of. But the thing is, because the star is restricted map, so the inverses actually of H as well as of G coincides. Okay. So that is also something you can actually take it as exercise. So what is the exercise? Okay. Once you know that H is a subgroup, let us say, so we use this notation H less than or equal to G to denote H is a subgroup of G. So, then you have this EH, which is the identity element of H. So, that should be same as EG. So, that is the first thing. The second thing, given A inverse, let us say with respect to H, that should be same as with respect to G for all A in H. So, these two things are very easy things to check. So, I will leave it to you to check. Okay. So, there are some easy way to actually check when something is a subgroup. Okay, we will come to that later, but let us first understand what happens in the group of integers. Okay, so now we have defined what is a subgroup. So, here I make this proportion. If something is a subgroup of this group of integers, then we have various equivalence conditions for that being subgroup. Okay. So, let us start with some examples of subgroups, then I will actually write down various characterization. So, you can see that if I take just a singleton 0, so that is already a subgroup, because 0 is actually closed under this addition. Okay, 0 plus 0 is 0 and inverse is there, and the restriction, if you do the addition to the 0 cross 0 to 0, that is a map. So, that means this is just a subgroup. So, you can just verify it. And then here is some non-trivial subgroups. For example, you can take all even integers, okay, which we denoted by 2z. So, this is what? This is set of all 2m, where m is coming from z. So, this also can be thought of the set of all even integers. So, this is also a subgroup. So, that is I will leave it to check, because addition of two even integers will be even and negative of even integer is even, and you can check this star when you restrict to 2z cross to 2z, it maps to 2z. So, then it is also becomes a subgroup. So, all those things satisfied. So, now what we are going to do, we are going to give various characterization. So, the first characterization is just the definition, the following are equivalent. So, start with A. So, it is a subgroup of G plus. So, note that A is being subgroup. Using this exercise, you can see that 0 must be in A. Okay. And the second exercise says, given any A in capital A, minus A also should be there. So, that means 0 is in A is equal to minus A. So, that is called symmetric subset. Okay. So, what are the conditions? So, A satisfies the following properties. So, 0 is in A, and then A is equal to minus A, and then if you think about the star being actually just map from A cross A to A, simply says that A plus A should be subset of A. Since A 0 is in A, this is equivalent to A plus A being equal to A, or otherwise just let me write it this way. So, A plus A is subset of A. Okay. So, A satisfies all these three properties. 0 is in A equal to minus A, and A plus A is subset of A. And the third thing, you can easily see that 0 is in A equal to minus A, and now since A 0 is in A, you can say that A plus A is A. Okay. So, now, so what is the fourth thing? So, that is more interesting. So, you can actually say that 0 is in A equal to minus A, and A plus 2A. So, that is also subset of A. Okay. Since 0 is in A, you can say that this is same as capital A. Okay. So, now the fifth thing, which is the most interesting part of the equivalence condition. So, given this capital A, if it is a subgroup, then there exists n in G plus such that A will be exactly given by NZ. So, it is not hard to check that this NZ, they are all subgroups, okay, and we are saying that the fifth one says that these are all the only subgroups, okay, of integers. So, what is G plus? So, G plus in our notation, these are all non-negative integers. So, that means 0, 1, 2, 3, etc. For us, n means they are all positive integers 1, 2, 3, etc. and Z means just all integers 0 plus or minus 1 plus or minus 2, etc. So, this is our notation. Okay. So, let us prove this. Okay, the proof uses what is called division algorithm. So, let us first see the division algorithm proof and then later we will actually come to the proof of this proportion. So, this proportion let us call it 1. Okay. So, to prove this proportion we need this following division algorithm. So, let me just state and prove. Okay. So, here is the division algorithm. So, let me state the division algorithm for first natural numbers, then later we can state it for integers, or otherwise one can state it for integers straight away, not a problem. So, what we do, we start with some natural number, let us say n, okay, and some integer a. So, then what we prove, there exists unique q, so coming from z, and R, okay. So, again it is also coming from Z, but that satisfies the following properties, okay, such that this A can be written as some NQ plus R with the condition that this R is strictly less than n and it is non-negative integer. So, this is the condition, okay. So, this A can be written as NQ plus R and where this R is the remainder, okay, modulo n. So, that can be at most n, it is non-negative and at most n, and this Q is called quotient, okay. So, this Q is called quotient and this R is called remainder. So, this is something you must have seen in school, okay, maybe without proof. So, maybe I will prove it for you, okay. So, now there are various cases that one is supposed to consider. So, most non-trivial cases when A is being non-negative integer, okay. So, maybe we can actually start with that and then I will explain what really happens. So, here is the proof. So, the very first case what we do, we assume that A is non-negative integer, okay. So, in that case, so there are following possibilities. For example, if A is 0, then you can take Q and R to be 0. So, there is no issue, okay. So, this is the sub case. So, if A is 0, so then you can take Q 0 and R 0. So, that works. So, we first prove the existence. So, this symbol I believe you must have seen. So, there exist, it means, so this is the symbol for there exists, and this exclamation mark. So, this is for the unique. uniqueness. So, this there exists with this symbol means there exists unique q and r inside each other, satisfying this. Okay, so when a equal to 0, it is clear that we can take q 0 r 0. So, then the equation that that we are interested in, this r is satisfied. So, for that purpose we can assume that actually a is non-zero. So, that means a is just a positive natural number. Now, know that again there are two cases. You can consider 1.1.1. So, I am writing it in very detail. I also want to teach you how to write mathematics. Okay. So, there are so many possible cases that appear. So, it is important to actually spell it out everything and then consider all possible cases. So, it is important to learn how to write mathematics. So, that is why I am just giving very detailed explanation here. Maybe that is something you should also learn over the time. Okay. Later, once the course progresses, I will not give you this much details. But anyway, so let us see the sub case 1.1.1, where you can assume that a is already smaller than n. So, this is positive, but smaller than n. So, then what you can do in that case? So, in that case, okay, maybe this case can be combined with a greater than or equal to 0 as well. So, maybe the first case you do not need to consider, this case you do not need to consider. For example, if this is greater than or equal to 0 and less than n, still you can take q to be 0. So, then take q to be 0 and r to be a. So, then you have a equal to q n plus r, where r is strictly less than, because r is a. So, this is satisfied. Okay. So, whenever a is strictly less than n, we can't really subtract multiple of n. Okay. So, there is nothing to subtract. So, we just subtract 0 multiple of n and then we just get the remainder. So, that remainder will be strictly less than n. That is what we are saying in this. Okay. So, now what will be the case 1.2.2? You can assume a is greater than n. So, this is the most interesting case. Okay. So, let us try to do this case and then we will understand what we really do. Okay, what is division algorithm is all about? So, basically you want to subtract multiple of n from a and then you reduce the size and then you reduce the size successfully, so that you come down to something that is actually smaller than n. So, that is what remains. Okay. For example, so let us pictorially understand. So, let us say you have a scale. So, let us say you are in this real line. Okay, and then you have 0 here and then you have a here and then you have n here. Okay. So, this is the scale which you are using, this is the n scale. Okay. And this is this a scale. So, you can see that. So, if you are trying to measure this scale of size a with scale of size n, then you can keep repeating that. Okay. You can just put this scale inside this and then you just start measuring. Okay. This is again another n scale, this is another n scale, like that you just put them here. So, then something will be remaining. Okay. So, it is very badly drawn. Let us take a here and this is your n, and then at some point you have another n and something remains here. So, that remaining thing cannot exceed n, because if it exceed n, then you can put one more scale of size n there and then cover it. Okay. So, that is why this remainder whatever that comes, that is actually should be smaller than n. So, this is the pictorial explanation. So, let us try to do algorithmically what we are doing, and then later I will tell you how to write down the clean proof. So, you start with A. What do you do first? You subtract n and then see whether it is less than n or greater than or equal to n. Okay, only those two are the possibilities. Now, so for example, if it is less than n, so then what will happen? A will become equal to a minus n plus n. Okay, then this becomes the remainder r, and quotient becomes 1, and this is your star, whatever we have written, this star. Okay, the q is 1. But what can happen? A minus n could be bigger than n. In that case, what you can do? You can subtract one more times and then see what happens. So, a minus 2n will be greater than or equal to 0, and then a minus 2n you see whether it is less than n or greater than or equal to n. If it is less than n, then you write a equal to a minus 2n plus 2n, then quotient becomes 2 and remainder becomes a minus 2n. Okay. So, this is what you are going to continuously do. You keep subtracting n from a, that means you keep subtracting multiple of n from a, and then you see when you reach some number that is smaller than n. Okay. And division algorithm guarantees that is always possible. Okay. So, that way you will be actually guaranteed that there is a quotient as well as remainder. Okay. So, algorithmically it is very clear, this is what we are doing, but how one writes down the proof. Okay. So, this is something you have to put it mathematically. So, whenever you want to write anything in mathematically, so try to construct sets that satisfy some property and then look for something, and then that whatever you are looking for will actually give you the result. Okay. So, here for example, we are looking for remainder and quotient. So, the best thing to do is what we can do, we can keep subtracting from a. So, I can look at all possible subtraction. For example, I can take a minus some q dash n. So, I can actually collect all q dash from natural numbers such that a minus q dash n is greater than or equal to 0. So, this set is well defined. Okay. So, because we assume that a is greater than or equal to n, so a minus n is at least greater than or equal to 0. So, 1 is there. Okay. So, note that 1 is in this set, and this set I am going to call it as capital Q. Okay. So, now note that this capital Q, okay, so this has to be finite. So, that is the most important thing. So, why it is finite? So, because this a is finite, n is finite. So, how many things you can subtract, how many multiples of n you can subtract from a, so that it remains actually non-negative. Okay. So, at least you can see that a minus q dash n is greater than or equal to 0 implies that a by n is greater than or equal to q dash, and this is a fixed rational number. So, that implies that this is actually finite. Okay. But I would actually recommend you to actually use only the properties of natural numbers to prove the same thing. I will leave it to you to think about it, but it is easy to prove that this q is finite. Okay. But I already gave you one proof. So, let me leave it as exercise, prove that q is finite. That means it cannot have infinitely many elements. So, now once it is finite, you can see that I can talk about max. So, the max q, I can call it q. So, what is the property of q? Q is in capital Q. So, that implies a minus q n is greater than or equal to 0, and q plus 1 is not in q, because q is the max. So, that implies a minus q plus n is strictly less than 0. So, that implies a minus q n is less than n. So, I can take R to be just this A minus q n. So, this is the remainder. Okay. So, R is A minus q n. So, then A equal to q n plus R, and then this R satisfies greater than or equal to 0, less than n because of this. Okay. So, if you think about it, indeed you can prove that q is exactly equal to 1, 2, etc. q. Okay. So, this is also something you can verify. So, but anyway, this actually proves the existence of q and existence of R for this particular case. So, that is when A greater than or equal to n. So, if you go back, we have considered all cases when A is non-negative. So, only the case that remains is A is actually negative. Okay. When A is negative, what we can do? We can simply take minus A and then apply the division algorithm. Okay. In case A is actually inside minus G plus. So, then what we can do? We can just take minus A. So, which is in G plus. So, then I can apply the division algorithm. Then I get n q plus R from the earlier argument. So, then you can see that then A will become n times minus q minus R. But the thing is, this R is less than or equal to greater than or equal to 0 and less than n. So, then what will happen to minus R? Minus R will be minus n minus R less than or equal to 0. But what we want? We want something that is actually less than. So, you can modify so that this R remainder is always between 0 and n minus 1. Okay. So, for that what we can do? We can simply just add and subtract 1 n and then see what happens. So, basically that is what we are allowed to add and multiply. So, add and multiply add and subtract the multiple of n. So, that is not a problem. So, you keep A as it is, n minus q, you just add n and then subtract n and then see what happens. Okay. So, look at n minus R. So, and then see what really happens. So, what you can do? You can just take A to be n minus q minus 1 plus n minus R. So, this I want to take it as remainder. So, what happens to n minus R? So, n minus R is actually positive. So, that is fine, and then why it is less than or equal to n. So, we want it to be less than n. So, yeah, this is less than or equal to n, that is because R is greater than or equal to 0. So, this is something we are getting for free. Okay. So, this is immediate 0 less strictly greater than n minus R less than or equal to n. So, now suppose this n minus R is equal to n, then again you can subtract one more n. Okay. So, again there are two cases. So, case 1 will be if n minus R is strictly less than, then we are done, there is no issue. And then case 2 will be what? If n minus R is equal to n, then you write A equal to n minus q minus 1 and then minus 1, you subtract and add. So, then this will become actually plus n minus R minus n, that is what you want to take, and then you add it. So, this will become 1. So, this will get cancelled. So, again you get minus q plus minus R. You want, this becomes 0 actually, because this is okay. In all these cases, you are able to actually produce q and R such that the equation star holds. So, there is no issue. Okay. So, this is actually happens. So, now in this case we need to prove the uniqueness. Okay. So, let us see how one can prove the uniqueness, and then I will stop. Okay. So, let us say you have two tuples q and r, q dash r dash, such that the same equation holds n q plus r, similarly n q dash plus r dash. Now, note that 0 will be less than or equal to r, and then r dash strictly less than n. So, these are all the conditions that you have. Okay. So, now what you can do, you can just assume q is greater than or equal to q dash, because you have the order property. So, this is without loss of generality, one can assume this. So, then in particularly n into q minus q dash will be same as r dash minus r, and this thing is multiple of n, and this is non-negative. In case this q is not equal to q dash, then this will be positive multiple of n. Okay, it is like 2n, 3n and so on. But on the other side, you have r dash minus r, both of them are strictly less than n. So, the difference will be definitely strictly less than n. So, that cannot be just multiple of n. That forces that q equal to q dash, and now q equal to q dash will force that r dash equal to r. So, this proves the uniqueness of the quotient and remainder. Okay. So, maybe I will take another 2-3 minutes and then complete the proof that I have actually guaranteed. So, if you go back to the proportion that I stated, and from the definition it is clear that A is being subgroup will immediately imply 0 is in A and A equal to minus A, and then A plus A is subset of A. Since 0 is in A is assumed, then this A plus A subset of A will imply that A plus A equal to A. So, so 1 implies 2 and 2 implies 3, they are obvious. Now, 3 implies 4 is also obvious, because if 0 is in A is there and A equal to minus A is already there, and A plus A is equal to A, then obviously A plus 2A, maybe you write it as A plus 2A is subset of A. So, that is obviously subset of A, and now 0 is there. So, A plus 2A is also equal to A. Okay. So, maybe you write it as 4 dash. So, that is 0 is in A equal to minus A, and then A plus 2A is equal to A. So, now 0 being in A, that is what implies A plus 2A subset of A immediately implies A plus 2A equal to A. Okay. So, 4 implies 4 dash is also obvious. So, what is non-trivial? The non-trivial thing is 4 dash implies 5. That means you assume that 0 is in A, you assume that 0 is in A equal to minus A, and then A plus 2A is equal to A or subset of A, does not matter. Okay. So, then we want to prove that there exists, we want to prove that there exists n in Z plus such that A equal to n Z. Okay, let us see how to prove this. So, what we do first, if A is 0, then there is nothing to prove, then there is nothing to prove. So, that is why we assume A is non-zero. So, if A is non-zero, so then that means there is something A in capital A. So, without loss of generality, I can assume A is positive, because A is equal to minus A. You take either A or minus A, one of them will be positive. So, I can assume that A is positive. So, now look at A intersection n, and this is non-empty. So, now what is well ordering principle says? So, it contains least element. So, I can talk about minimum of A intersection n, that you call it n. Okay. So, the minimum of this you call it n. Now, note that A plus 2A is equal to A and A equal to minus A. So, what it says? It says minus n is in A, okay, and then n plus 2 minus n. So, sorry, that is yeah, 2 plus n you take. So, that means 3n. So, 3n is in A. So, now you take n plus, okay, 2 times 3n. So, that will be 6 7n in A, and similarly you can also take 2 plus 2 7n, that will be like 14n and so on. So, now what we claim, so we claim that, okay, first of all nz is a subset of A. So, this is our first claim. Okay. So, this we want to prove that for using these things. Okay. So, since A is equal to minus A, it is enough to prove only the positive multiples are there. So, that is what we are trying to prove. But A plus 2A is equal to A already implies that 3n is there, 7n is there and so on. Okay. So, we want to get twice n and so on. So, and then we see how it can be done. Okay. So, let us start with, yeah. So, let us start with some element A. Okay. So, this is one thing that we need to claim. The another thing that we need to claim is A is also subset of NZ. Okay. So, you start with A in capital A and then see what happens. So, now since A is in capital A, so you can actually write it this A as some 2qn plus r, with the r is being less than n, okay, sorry, less than 2n. So, now what we know? We know that A minus 2qn, which is r. So, this should be in capital A, because A plus 2A is A. So, A plus 2A is A. So, that implies if I take any multiple of, okay, even multiple of n, okay, if I add it with this A, so that A minus 2bn should be in A for all A B in A. So, that is easy to see. Okay. Any even multiple, if I add or subtract, so that has to be inside capital A. So, that means this R should be in capital A. But note that this R cannot be strictly less than n. Why? N is the minimum that we have already chosen. Na? So, n is the minimum among all A intersection n. So, that means this cannot happen. So, that forces that n should be at least R, okay, and then R is less than 2n. So, this is what you have. So, n greater than or equal to, sorry, less than or equal to R, less than 2n. So, that you have. So, now if n is equal to R, then what happens? A will become multiple of n. Okay. So, if n equal to R, so then A will be inside NZ. So, that is the case that we want to claim. So, that will be done. But n may not be equal to R, then let us see what happens in that case. Then n becomes greater than R and less than 2n. Okay. So, then if you just subtract by minus n, then what do you get? So, let us subtract by minus 2n. You get minus n less than R minus 2n less than 0. But note that R is in capital A. So, that means R minus 2n is also in capital A. Okay. but since this is less than 0, 2n minus r which is greater than 0, this 2n minus r is also in capital A. But what will be 2n minus r? So, 2n minus r is positive, okay, and strictly smaller than n. So, 2n minus r is positive and strictly smaller than n. So, that forces that we get a contradiction. We get a contradiction. Why we got contradiction? We assume that n is not equal to r. Okay. So, because n is the smallest element that is inside A intersection n. So, we have produced something smaller than that, that is in capital A, and it is positive. So, that we got because we assume that n equal to r. That means this A that we have taken, that has to be always inside NH. And now A is actually contained in NZ and n is inside A and A plus 2A equal to A. Now, using this we want to prove that NZ is equal to A equal to NZ. Okay. So, let us do step by step and then we can actually reach. So, you have n is in A and then A plus 2A is A and A is also equal to minus A. Okay. So, that means minus n is already in capital A. So, that is fine. So, now you take 0 here in A. So, then 0 plus 2n. So, that is in A plus 2A. So, which is A. So, that implies 2n is in capital A. So, now if you take n plus 2n, okay, so that is inside A plus 2A. So, which is A. So, that implies 3n is in capital A. So, like this, so I will leave it to you to complete the proof. You can prove that any positive multiple of n is in capital A. Since A equal to minus A, that would imply that NZ is subset of A, and that would imply that A equal to NZ. Okay. So, indeed what we have proved that any subgroup of integer must be of the form NZ. So, on the way we actually gave various characterization of these subgroups. One important particular characterization is that it is enough to have just 0 is in A and A is symmetric and A plus 2A is equal to A. So, now I will leave it as exercise to think about. So, you take some subset of integers again and then satisfying the following conditions. 0 is in A and it is symmetric. So, now you assume that A plus 3A is equal to A. Okay. So, now this is the condition is given. So, my question is, what can you say about capital A? Okay. And similarly, the same question you can ask for other types of relations. Okay. So, note that if A is subgroup, okay, if A is subgroup, so then you know that any MA plus NA, so this will be subset of A for all M and N from Z. Okay. So, this is very strong condition. So, this maybe you can take it as exercise and then you can prove this. So, then we have any multiple of, that means any MA plus NB should be in A for all So, let us fix that mn. So, then for all, yeah, if even if you vary it is okay, for all mn in z and ab in capital. So, this is what we want to throw. Okay, so this gives some information about subgroup of integers. Okay, so with this I will stop here, we are running out of time, and then I will continue with some more groups that actually comes from this elementary number theory called arithmetic groups, okay, modulo n. So, with respect to addition modulo n as well as with respect to multiplication modulo n, we can talk about some groups. So, we will see that in our next lecture. I will stop here. Thanks.